talked a little bit about the resistance equation that we got from Dr. Poisson, and the equation looked a little bit like this. So we had, actually, let me just replace this. We had 8 times eta, which was the viscosity of blood, times the length of a vessel, divided by pi times the radius of that vessel to the 4th power. And all of this put together gives us the resistance in a vessel. So thinking about this a little bit more, let's assume for the moment that the blood viscosity is not going to change. Certainly won't change from moment to moment, but let's say that in general blood viscosity is pretty constant. Now, given that, if I want to change the resistance, then I have 2 variables left, right? I've got the length of my vessel, and I've got the radius. So if I have a vessel like this, and let's say it's got a certain radius and length, and let's say that radius is r, and the length is here, and I apply a number, let's say the number is 2 for the resistance. Well, I have 2 options for changing that resistance. If I want to increase the resistance, I can do 2 things. So let's say I want to increase that resistance. And you can look at the equation and tell me what that answer would be. 2 things. And I'll actually draw it out. So one thing would be to keep the radius basically the same, but make it much longer, right? Because if I make it longer, then since the L is now, let's say, twice as long, and the R is the same, now my resistance is going to double. So now we go 2 times, and 2 times 2 is 4, so my resistance is 4. Okay, option 2. Let's say I don't want to change the length, so I keep the length the same. Instead, I could actually maybe change the radius, and let's say I half the radius. I make it half of what it was. And I actually worked out the math in the last one, and it turned out that if you half the radius, in the last video that is, then the resistance actually is 16 times higher. And you can see that because the resistance equals r to the 4th power. Here, r is to the 4th power. So because r is to the 4th power, when you half it, it goes up 16-fold, and so 16 times 2 is 32. So my resistance is 32. So these are the 2 strategies, if you think of it that way, that a blood vessel can use to increase resistance. And of the 2, you can see that one of them is definitely more effective. I mean, I can see that because it's raised to the 4th power, this is going to work much more effectively to raise resistance than changing the length. And additionally, if you think of it kind of from a practical standpoint, keep in mind that I have smooth muscle, so it's actually pretty easy to accomplish this, or at least possible to accomplish this. Whereas trying to actually change the length, which is option 1, is not feasible, right? I mean, it's much, much more complicated to actually expect a vessel to simply double in its length because it wants to raise resistance. So for multiple reasons, changing radius, again, becomes the name of the game. Okay, so let's complicate this a little bit. Let's say instead of 1 vessel, I've got 3 vessels. I've got, let's say, 1 vessel here, and the resistance is, let's say, 5. And then I've got, let's say, a longer vessel here. And this one happens to have a resistance of, let's say, 8 because it's longer. And let's do same radius for all these, but shorter now. This one is 2. And I want blood to flow through all 3 of these. What is my total resistance? And here we're talking about the 3 vessels being in a series, meaning that you actually expect the blood to go through all 3 of the vessels, or tubes. So if they're going to go through all 3 tubes, what you have to do is simply add up the total. So resistance total, so this is total resistance, and I just put a little t to remind me that that means total. So total resistance equals the resistance of 1 part plus the 2nd part plus the 3rd part, and if you had a 4th or 5th part, you just keep adding them up. So in this case, you have 5, 8, and 2. So RT becomes 5 plus 8 plus 2, and that equals 15. So total resistance would be 15. And actually, I'm going to give you a general rule. So total resistance is always greater than any component. And you can see how this is very intuitive, right? I mean, how could you possibly have a situation where if you're just simply adding them up, because we don't expect any negative resistance, in this situation. You're simply adding up all these positive resistances. Of course the total will be always greater than any one component, right? Seems intuitive, but I just wanted to spell that out. So now, let's take a scenario where you have a human body, a vessel in the body, and let's say you have 3 parts to it. And these are equal parts. So let's say the resistance here is 2, 2, and 2. And you have, obviously I want to calculate as before my total. So my total will be 2 plus 2 plus 2, which is 6. And then an interesting thing happens. So you have, let's say, I'll draw the same vessel again. Really interesting thing happens. This is the same blood vessel, but now you have a blood clot. And this blood clot is floating through the blood vessels, and it kind of makes its way to this one that we're working with. And it goes and lodges right here. So right here, you have a lodged blood vessel. Wow, that's pretty big, but it's right in that middle third of our vessel. So we have now a tiny little radius here, right? It's about, let's say, half of what we had before. So this is the new radius. It equals half of what the old radius was. And from the last example, that's going to increase the resistance in that part by 16. So the resistance here stays at 2, here stays at 2. But here in the middle, it goes from 2 to 32 because it's 16 times greater. So you end up increasing the resistance in the middle section by a lot. So let me just write that out for you. So 2 times 16 gets us to 32. So here the resistance is 32. And so if I wanted to calculate the total resistance, I'd get something like this. 32 plus 2 plus 2 is 36. So I actually went from 6 to 36 when this blood clot came and clogged up part of that vessel. So just keep that in mind. We'll talk about that a little bit more, but I just want to use this example and also kind of cement the idea of what you do with resistance in a series. Now let's contrast that to a different situation, and this is when you have resistance in parallel. So instead of asking blood to either kind of go through all of my vessels, I could also do something like this. I could say, well, let's say I have 3 vessels again, and this time I'm going to change the length and the radius. And let's say I have, this one's really big, let's say. And the resistance here, let's say, is 5, here is 10, and here is 6, right? So you've got 3 different resistances, and the blood now can choose to go through any one of these paths. It doesn't have to go through all 3. So how do I figure out now what the total resistance is? So what is the total resistance? Well, the total resistance this time is going to be 1 over 1 R1 plus 1 over R2 plus 1 over R3. And you can go on, just as before. But in this case, we only have 3, so let's just put that there, and that there. And I can figure this out pretty easily. So I can say 1 over 6 plus 1 over 10 plus a fifth. And the common denominator there is 30. So I could say 5/30. This is 3/30. And this would be 6/30. And adding that up together, I get 1 over 14/30, or 30 over 14, which is 2 and let's say 0.1. So 2.1. So the total resistance here is 2.1. Putting all 3 of these together. Pretty interesting. And I want you to realize that the resistance in total is actually less than any component part. So unlike before where we said that the total resistance is greater than any component, here an interesting feature is that you have total resistance is always less than any component. So pretty cool set of rules that we can kind of go forward with.